Once again, a very good evening to all of you. This is your course instructor, KHUSHWANT FATNANI. So today, in today's session, we are going to see the chapter Thermodynamics, and the chapter will be done in a way so as to make sure that we are able to properly revise the concepts from the chapter according to the past year coverage, right? So let's start off. Okay, so here we go. Right. Okay. So let's begin. Today we are taking the chapter, revision of the chapter Thermodynamics, right? So we'll quickly see what are some of the important concepts and then plunge into the numerical solving, right? So the chapter Thermodynamics comprises of some basic terminologies and basic definitions first, and then the chapter introduces you to some laws, some kind of engines, right? Carnot engine, etc., etc., right? So let us see what are the topics and what is the distribution of this chapter. So every year, first let's see the distribution. Every year in every shift, every day, whenever the shifts are there, you will find 1 to 2 questions, right? 1 to 2 questions from this chapter, which appears in JEE mains, right? And there is almost a similar pattern observed in NEET examination also, right? So every year you'll find 1 to 2 questions from this chapter. Mostly JEE gives one question, JEE main gives one question, whereas NEET provides you sometimes 2 or more questions also, right? So this is how the chapter is distributed in terms of number of questions being asked, distribution, right? Now let us see from the chapter the topics. So the main topics that you have studied in this chapter are, first one, you must have read about from this chapter the laws of thermodynamics, the laws of thermodynamics, right? So we have the laws of thermodynamics. I'll write thermodynamics as TD, right? So in the laws we read 3 laws one by one: 0th law, right? First law and second law, and their applications one by one, right? So we are also told about different thermodynamic processes which are available, right? We are told about different thermodynamic processes. Then another next important part, we are told about reversible and irreversible processes. Reversible and irreversible processes. I would request you all to please jot down all of this, whichever is up, whatever content is appearing on the screen. So this is going to help you when you are reading and revising your notes, right? So reversible and irreversible processes. Then the next one, next important topic from this chapter is the one which discusses the application of the second law, that is concept of heat engine, right? Carnot engine, we also read about its efficiency, which I'm denoting by the letter nu. Then we study about refrigerators. From this chapter, you get a lot of questions sometimes which are based on graphs, right? So graph related questions. Type of questions which are asked. questions related to graph, that you'll be given so and so process is happening, identify or find out one or more number of variables, right? So questions based on graph. This is one. Second is you get questions based on phase change. So phase change are the kind of questions where you talk about the facts like the ice is melting, how much heat will it absorb, right? Or maybe ice is turning to water, then water's temperature is rising and later it is turning to steam, right? So how much heat is absorbed or the vice versa process is done, right? So about phase change basically, right? So questions based on phase change are also asked. A lot of graph questions are very frequent in JEE examination, right? And so is the case with NEET examination. We have a lot of questions every year which are asked based on so these phase change questions are the ones which are basically relating to calorimetry. So maybe I can also put it under a separate head, third one as calorimetry. Right, so in the principle of calorimetry, you have the amount of heat given by a body is equal to the amount of heat absorbed by another body, right? So the questions with regards to calorimetry are also very frequently asked in your examination. Then there are another questions which are related to heat transfer by conduction. Heat transfer by conduction. So there is a law, I hope you all know, that rate of heat transferred, right? Rate of heat transferred, which can be also called as H or Q per unit time, right? Q per unit time is given by difference of temperature upon thermal resistance, or L by Ka, where L is length of the entire conductor, A is the area of perpendicular cross section area, and K is the thermal conductivity, right? So this is also what is called as thermal current. This rate of the heat transfer is also called as thermal current, or rate of heat transfer. That is, at what rate heat is being conveyed from one part of the material to another, right? So this is rate of heat transfer. Very beautiful questions are made on this aspect, right? Rate of heat transfer. So what kind of questions? Suppose you are asked to find out what is K effective, right? What is K effective if so and so materials are connected together? And when I talk about graph based questions, suppose you have been given a graph, right? Let's say something like this. A process is happening where we know this is a graph between pressure and volume. This is point A, for the initial part of the line, and the last point is point B, right? You might be given some values and you'll be asked to find out that what is the, maybe perhaps like what is the maximum temperature of the process, etc. Like questions of this sort, right? And you will be given the values of P, V and T at A and B, right? So graph of this sort are asked, or the questions based on such concepts are frequently asked in your examinations. Then there are also several questions which are based on the concept of specific heat capacity, right? These are next variety of questions. Or heat capacity, specific or just heat capacity. That is at constant pressure, constant volume, Cp, Cv, right? So these are some, on a general note, what kind of questions that you might face in your examinations, right? Mostly whatever I have covered on this screen, right, you will get almost all type of questions in your examination. One more type which normally pops up is also Newton's law of cooling. Very frequent. Newton's law of cooling. This also you might see in your paper, right? Very often. So class, just have a note of these questions, especially also very important, the Carnot engine based questions, right? Have I written them? Yeah. So calorimetry also, right? The questions based on Carnot engine. Carnot engine and refrigerator, right? So the process is happening in them, temperature of the sink and source, etc. Right? So these are some basic concepts on which they test you in the examination. You need to be prepared with the same, right? So class, kindly note all of this down so that we can then accordingly begin with the revision. Yes, class. Once you have noted whatever I have written on the board, please raise hand so that I will know that you have written this down and we can move to the formulas, concepts, and the questions. Yes. Please jot this down, whatever I have written on the board. So on the right side, on the left side, you will find some basic, some main questions that appear. On the right side are the variety of questions that you will find in exam very frequently, right? Yes, class. Get going. Once you are done, raise your hand. Yes. So Karuna, Atul, and Anukriti have written this down. Fire and Mahila are yet to. Okay, get going. Yes, Ambik. Yes, Mahila, are you done? All right, I think everyone is done. Everyone can bring their hands down. Thank you, class. Let us proceed. So, dear all, let us see a quick recap of whatever concepts you all have been given in this chapter, right? Kindly jot this down in your lecture notes, right? So we'll begin, right? So the first kind of concept that you have read in this chapter is the first law of thermodynamics, telling you that whenever there is a system, right, and you're giving some heat to the system, there is a system, you give some heat to it, let's say, and you denote it by delta Q. So heat given to the system, right, to the system. Heat given to the system changes to increase in the internal energy of the system, delta U, plus work done by the system. Very important. Work done by the system. Class, remember whatever quantities I have written here, right? So be it increase in the internal energy, I'm denoting increase by this upward arrow, increase in the internal energy, work done by the system, or the heat given to the system. All of this, all these three quantities, internal energy, right, and the heat given to the system, all of these are taken as positive. Please note it down. So this is the sign convention that you follow, right? This is the sign convention that you follow. So we are seeing a recap of the chapter, right? Okay. Now, the next part is you have this quantity called as work, right? Work is defined in two ways. If if it is done at constant pressure, right? At constant pressure, its value is changed by some means, but in general, you define it in this integral form. Work W is given as integral of P dV. Integral of P dV starting from an initial value of Vi to a final volume of Vf. So we all already know that integral y dx tells me the area under the curve. Let's say I have a graph between y and x. So this area under the curve, right? Let's say this is some curve. So this area under the curve right? So this area tells us, the one which I've shaded in pink will therefore will be telling us about integral, or with this area is equal to integral y dx, right? So similarly, if you just replace y by p and x by v, that is volume, we will get a p versus v graph, right? And this p versus v graph area will give us integral p dv, or work done. Simple, right? Right. So this will give us integral p dv, or work done. Right. So everyone may note this down. Right. Very simple. Then next recap is talking about the value of Cp and Cv in terms of adiabatic constant and universal gas constant. So we all know that this is called as adiabatic constant. Adiabatic constant, right? And is given by, it is a ratio, which is the ratio of specific heat capacity at constant pressure and specific heat capacity at constant volume, Cp by Cv, right? And we know that R is universal gas constant. R is universal gas constant. And Cv is therefore given as R by R upon gamma minus 1. R by gamma minus 1, right? We also have Cp, right? Cp from this formula. See, Cp will be equal to gamma times Cv, correct? So from here, you will have gamma times Cv, and just substitute the value here. You'll know that Cp is equal to R gamma upon gamma minus 1, right? I hope you all are clear with this. It is just a quick recap, right? Similarly, the relation between Cp and Cv, Cp minus Cv is equal to R, or universal gas constant. Next one is that whenever we are given with a mixture, also these kind of questions are sometimes, you can see them popping up in your exams, right? You will be given that, let's say, I'll first give you the formula. So it says that Cp or Cv or any kind of C, right? Take this for both Cp and Cv. The net C of a mixture is given by N1C1 plus N2C2 whole by C1 whole by N1 plus N2. Whole upon N1 plus N2. Where what are N1 and N2? So let's say I'm taking two gases and mixing them together, right? Two ideal gases, and I'm mixing them together. The number of moles of first gas is N1, number of moles of second gas is N2. The specific heat capacity of first gas is C1, second gas is C2, right? It can be at constant pressure or it can be at constant volume. So this formula is applicable for both Cp and Cv, right? The net value of Cp or Cv for the mixture, right? Net value for the mixture, Cp mix or Cv mix, will be given by this formula, right? So this is how we get the Cp or Cv of the mixture. These are also some questions which very frequently pop up. So class, if you have written this down, whatever I've written on the board, please raise your hand so that I can move to the next page. Yes, class. As you are done, raise your hand so that we progress to the next page. Yeah. All right. Right. So let's see the questions right now after this and some more important formulas which will come to use. So you can bring your hands down, class. Thank you. Right. Yeah. So the next ones are, you are given here, we read, as I just told, different kind of thermodynamic processes. See, so we have different laws of thermodynamics, right? And we see different thermodynamic processes. So what are different thermodynamic processes that we come across? The thermodynamic, one of the very important thermodynamic processes is first one. So let's say we have three variables, right? P, V and T, which we generally deal in. So we'll take one by one each one of them as constant, and let's say the next thing that is important is heat. So we'll also take heat as constant, and therefore we'll have different thermodynamic processes as first one, isobaric. So we are talking about different thermodynamic processes and their respective representation on a PV graph, right? So I'll make a PV graph on the RHS. And the respective processes on the LHS, right? This is a pressure versus volume graph. Pressure is on the y-axis and volume is on the x-axis, right? We have first one, let's take pressure constant. So it will be called as, you must have rightly guessed, isobaric process. Isobaric process where pressure is constant, right? It is, on an obvious note, this will be represented by a straight line which is horizontal to the base where pressure is constant. Let's say pressure is P naught and constant all through the process, right? So this blue line is telling me isobaric process, right? Let's take the next one. For the next one, we'll take volume constant. It will be called as isochoric process, right? Isochoric process. In this, volume is constant. Similarly, there can be a process in which, so before we go ahead, isochoric processes will be represented by constant volume. You must have guessed, yes, it will be represented by a vertical line such that the volume is constant. Let's say it is V naught, right? Next one is third, that is isothermal process. Class, just make this as a mark, isothermal process. You can also write these in terms of the ideal gas equation values, right? So we know that ideal gas equation is PV is equal to nRT, right? So if when pressure is constant, I can write T upon, from here, when pressure is constant, just write P, then T by V will be constant. T by V will be constant. Similarly, one more derivation from here, that when volume is constant, pressure is directly proportional to temperature, right? And when temperature is constant, PV will be a constant, right? Or P is inversely proportional to V, right? This happens when temperature is constant for an isothermal process, correct? Let's mark this on the graph. This is an inverse relation or a hyperbolic relation between the two variables. So this is the one which I have represented in the green line given as isothermal process. Isothermal process, right? Next one is, let's take, we have taken these two now. Next one is adiabatic process. See, taking heat as zero, heat exchange as zero. Adiabatic process. A process in which there is no heat exchange or delta Q is zero, right? Because heat is a dynamic form of energy, that is, which is moving from one body to another. Only then it can be called as heat. So if the net heat transferred from one body to another is zero, then we can call that process to be adiabatic, right? And here for an adiabatic process, delta Q is zero. Plus, for all of these processes, we can also report the value of C, right? So let's say I want to write the value of C for all of these processes. I'll rub this. And what is C? I'm talking about specific heat capacity. See how we'll write it, right? So I'm reporting the values of C for all of these processes. Let's say I'll write C here, right? We know the formula of heat in terms of specific heat capacity, right? Heat transferred is mc delta T, right? Mc delta T, correct? Now, if the ones which are very simple, we know, right? Isobaric, pressure is constant, then it's called Cp. Isochoric, when volume is constant, it's called Cv, right? Correct? Similarly, how will it be given? Very simple. Cp will be equal to heat transferred at constant pressure upon mdt. Similarly, Cv will be equal to heat transferred at constant volume upon, instead of mdt, you can also write as ndt, where n will be the mass, n will be the number of moles instead of m. So you can also write n or number of moles. So ncdt, right? So you'll have n upon ndt. Similarly here, upon ndt. Let's write the next ones. So you have isothermal process. Now for the isothermal process, the delta T or change in temperature is zero. Since change in temperature is zero, just have a look here. C is inversely proportional to 1 by T, given the heat transfer is taken as constant. So if delta T is zero, C will tend to infinity. See, the C value will tend to infinity if delta T is tending to zero from this equation, right? Therefore, for an isothermal process where change in temperature is zero, the specific heat capacity is infinity. See, such an important fact. Similarly, let's say we are talking about an adiabatic process. So for an adiabatic process, delta Q value will be zero. Therefore, we'll have, instead of delta Q, so this was for an isothermal process. Let's say we are talking about an adiabatic process. So for an adiabatic process, we have delta Q is equal to zero, which implies NC delta T is zero, right? This implies that C is equal to zero. So for a process in which there is no heat transfer, specific heat capacity value is zero, right? So this is how we talk about them, right? The last one, adiabatic process, right? How do we display an adiabatic process on the graph? So this is very peculiar thing, class. Let's say the green line, the red line is telling us the isothermal process. So an adiabatic process has a slope which is greater than the slope of an isothermal process, right? So let's say we are talking about points A and B and C on the graph, right? You can clearly see that there are two graphs, right? Now let's say I'll draw a tangent to both of these graphs, right? Let's say I'll draw the tangent to both of these graphs at a point. Let's say over here and then over here. So I can very well see that the slope of the tangent, or maybe I'll draw another one. Yeah. So the same point, if I draw tangent on both the curves, one was isothermal curve, this one, this is isothermal curve, and the one which I've drawn in black, this one, is an adiabatic curve, right? So what happens is the slope for, take this as a note, class, the slope for, I'll represent the slope as maybe m, right? M is equal to slope. M is slope. So the slope for adiabatic curve is given as gamma times of the slope for, or m for, an isothermal curve. This is something so crucial, class, to understand that slope for an adiabatic curve is always larger, as you can see in this graph, right? As you can see in this graph, when we are moving from a low to high volume region, as the volume is increasing, right, along the process. So there is a quicker fall in pressure, right, for the same change in volume. So I hope you all have written this down. Once yes, please raise your hand. Yes, class. So the higher is the slope, the steeper will be the fall in pressure, right? If you all have written this down, please raise your hand. Yes, class. Whatever is written on the screen, if you have written it down, please raise your hand. Yes, class. So we have Anukriti, Atul, and Karuna yet writing. Once you're done, let me know so that we can move. Okay, great, great. Class, thank you. You can bring your hands down. I think everyone is done. Let's take something very important. One of the very crucial processes, class, is called as polytropic process. Have a note. Polytropic process. It's called a polytropic process. Please jot it down. Polytropic process. Right? Please jot it down, class. So what is a polytropic process? Let's say we have all of these processes defined with one or the other symbolic way. Now let's say I am representing a process in terms of pressure and volume as PV power n is equal to constant, right? PV power n is equal to constant. This adiabatic process, by the way, is represented at PV per gamma as a constant. In terms of pressure and volume, we represented an adiabatic process as PV is equal to PV per gamma is a constant, right? So in a similar fashion, if instead of gamma, we have some other number, let's say n, right? Such a process is now called polytropic process, right? Polytropic process. So for a polytropic process, class, we just saw how do you calculate specific heat capacity. Now, many a times, not once, class, I'm stressing this point, not once, but many a times, you are told that for a polytropic process, find out specific heat capacity C, right? So the specific heat capacity C for a polytropic process is given as C is equal to CV for that gas, right? For that ideal gas, C is equal to CV plus R by 1 minus N, plus R by 1 minus N, where R is again universal gas constant and N is the exponent of the term volume or the volume term V, right? So class, just jot this formula down, a very crucial formula, right? A very, very crucial formula and a very high expectancy that you will get such a question in this year's examination. Again, a very high expectancy that you will get this question in this year's examination, right? Such kind of question in this year's examination. A very probable or most probable question. Kindly jot it down, class. Very, very probable, right? Please mark my words. Such a concept is very frequently asked in your examinations. Just stay alert. Okay? All right. So I hope you all have written it down until here about polytropic processes. Now, something of very paramount importance is the formula or the concept of work done, right? So for all of these processes, you have different work done, right? And also it's important to understand the difference between, or the difference between an adiabatic and isothermal process and other kinds of process when we are talking about work done. So let's understand that with the help of a graph. A better term would be, let's revise that with the help of a graph. So let's say we have again a graph between, what are we seeing? We are seeing the work done. How is the work done varying, right? So we are seeing how is the work done varying for different kind of processes, for different processes. What did we see now? Just some time back, we saw that work is nothing but area under the curve. Which curve? PV curve, right? Area under PV curve, right? So now since we have the information about different kind of processes, let us see how is the work done varying for these processes. So let's say we have a point here, A, okay? Now we are moving from this point to another point, let's say B, okay? And that process is the first one which we had taken, constant pressure process, see? Or an isobaric process. So in an isobaric process, class, the work done is maximum. So I'm writing work done at constant pressure is maximum, right? We had the general formula for work done as integration of PdV, right? So now this work done is no longer integration of PdV because P is constant. Every constant comes out of the integral. Therefore, this becomes P times of delta V. Always remember, class, this delta word means final minus initial. So wherever you put this delta word with another variable, you will have V final minus V initial. Note it down, class. Okay. Now, let's take one more thing. Let's say we have another process given by, as we had just told, let's take an isothermal process, right? An isothermal process. So an isothermal process. Let's say I'm defining an isothermal process with this red color graph. So see, the work done will be this area. I'm shading it, right? Have a look. The work done in an isothermal process will be this one. All the area under the graph, right? Correct? So now, class, this area is representing me. This area is telling me that the work done in an isothermal process is much less than the work done in an isobaric process. So just have a note of it, that the maximum work done, take this as a note, that the maximum work done is always in an isobaric process, whereas for an isothermal process, the work done is lesser. Isothermal process, the work done is lesser. Especially what kind of work? We are talking about expansion work. See, because the volume is increasing, we are going to the right? We are going to the right for different. So this is work done for different thermodynamic processes. And more importantly, we are talking about expansion. Very important, expansion. Right? So this is an isothermal graph. Now we have seen the isothermal and isobaric graph. Similarly, We can also see the curve for adiabatic. We just saw that the slope of an adiabatic is larger. So here is the curve. Let's say we are drawing a curve for an adiabatic process. It would have, this will have a higher slope, right? So this angle value theta will be larger, right? Whereas this angle value theta will be smaller. Therefore, since theta is small, tan theta is smaller. For an isothermal curve, tan theta is smaller means slope is smaller, right? And we just saw here that the slope of an adiabatic curve is equal to gamma times of slope for an isothermal curve, and this gamma value is greater than 1. Since gamma is greater than 1, the slope of adiabatic is greater than the slope of isothermal. You can also take this as second note. Slope of adiabatic is greater than slope of isothermal. Right? Okay. Have a look, class. Now, let me erase these points. So I hope you all have noted this down, right? So that we can move ahead. Now, we had two processes already. We have seen isothermal, three in fact, right? The first one was isobaric. This was isobaric. Then we saw isothermal. We have also seen next one as adiabatic, which has a higher slope, and therefore its pressure, final pressure volume is value is low, right? Adiabatic. So this graph, class, you should have a very sound understanding of this graph. See, suppose I can frame a question that a gas is undergoing, class clearly listen, a gas is undergoing a gas is undergoing a rise in its volume. That is, there is an expansion, right? Expansion such that the pressure falls, One path is isothermal, another path is adiabatic. They can ask you if the pressure becomes P iso in case of isothermal process, whereas if it becomes P adia in terms of at the end of an adiabatic process, which is larger, or what is the relation between P iso, that is end pressure in an isothermal process, and an end pressure in the adiabatic process. Which one is larger? You can clearly see which one is smaller, which one is larger. We can see that the fall of pressure, let's say the initial pressure was P naught. So the fall in pressure is higher. Fall in pressure, or delta P, is higher for adiabatic than the fall in pressure for isothermal. Such several questions are based on this format. You should have a very good understanding of these graphs. Super important. Similarly, you can also see that the final pressure values, when I'm talking about the final pressure values, of course, the fall is higher in adiabatic. That means the final pressure will be lower. I will repeat. See here, the fall in adiabatic is higher. Therefore, final pressure will be lower, right? So we will write this if we are talking about final pressure. If final pressure values are what we are talking about, then the pressure in adiabatic is lower than the pressure in isothermal. Have a look and note this down, class. Take this maybe as third and fourth notes in your copies, lecture notes. Right? Class, as you're done writing everything on this page, please raise your hand so that I can move to the next one. Yes. also note class, there is a specific kind of process called a cyclic process. There is a specific kind of process called a cyclic process. Very simple. If I have a graph, if the initial and final state become the same, I will repeat, I start from a state, okay, and then I come back to the same state. Let's say I start from A, then I go to another state B, right, and come to next thermodynamic state C, right, and then maybe C, I'm coming back to A, right. So this entire process will be called as cyclic, right. And for a cyclic process class, since initial potential, initial internal energy and final internal energy are same, we call delta U value is 0. That is, the change in internal energy for a cyclic process is 0. Note it down, class. Please note it down. Change in internal energy. So this is basically telling you that there is no change in internal energy. Why? Because internal energy is a state function. It depends on the state of the body, and these three, A, B and C, are states. The A, B and C are states, and internal energy U is a state variable or a state function. It depends on the state of the body, the PVT values of the body, and more particularly temperature value. When you talk about the numerical examples, this U is called as a state variable and is supposed to be a direct function of temperature, right? Because of that, since delta U is 0, we also say one more thing, that I'll just write it down here. In what all cases delta U value can be 0? What all cases delta U value can be 0? This becomes very handy when you're solving numericals. I'll repeat, delta U value. So we have, that is, change in internal energy can be 0 in two cases. Just now we saw one, when the process is cyclic. When the process is cyclic, that is, the entire gas system is coming back to the same position. I will repeat, the entire ideal gas system is coming back to the same position or the same state. If that is happening, then it is a cyclic process and delta U is 0, one case. Second case, because U is supposed to be a direct function of temperature, absolute temperature. So whenever the temperature changes 0, that is, the gas is undergoing an isothermal process. That is, when the temperature is not changing, when the temperature is constant, then we say, or when delta T is 0, we say that delta U is also 0. So note it down, class. It can be either a cyclic process or it can be an isothermal process in which the change in internal energy is 0. Change in internal energy is 0. So you have a law, right? First law. Let us recall that. Heat energy supplied changes to internal energy and work done, correct, by the system. This is work done by the system. This is heat energy supplied to the system, correct? And this was the rise in internal energy of the system. Now, since delta U is 0 for these two cases, that is cyclic and isothermal. Cyclic and isothermal, delta U is 0. So when you take delta U to be 0, what do you get? You get that, you're right, all the heat energy which is supplied to the system, class, I'll repeat, all the heat energy which is supplied to the system changes into work done by the system. All the heat energy supplied to the system changes to work done by the system. When does it happen? When the process is cyclic or isothermal. Super important fact. Please jot this down, class. One more thing which is quite important to learn, that when the process is isochoric, isochoric we have just read. See here, class, isochoric means the volume is constant. So we will have this way. Just have a look. See, along the orange line, let's say volume is not changing. That is, it is constant. So we'll say let's say it is equal to V naught. Let's say it's not changing, right? So such a process will be called as isochoric. Of course, this is a line, so there is no area under the line, and therefore work done in an isochoric process will be zero. Very important. This is an isochoric process. So let's write down the expression of work done for each one of them. All the kind of processes we learned, work done expressions, right? So one by one, we'll write the work done expressions. Let's say first one, we'll take it for very simple and isobaric process. When the pressure is constant, P is constant. And class, you all should remember that the general formula is always W is equal to P integral dV. We just learned, right? W is equal to P integral dV. The general formula is always this. And when pressure is constant, work done becomes P dV, right? Similarly, when volume is constant, the process is called as isochoric, right? And the work done is given by 0. Why? Because delta V value is 0. So for an isochoric process, it's 0. Similarly, the next one, let's talk about isothermal process. Isothermal process. That is when what is constant? So here I will just write isothermal. Let us write here that volume was constant. Whenever temperature is constant, T is constant, then we have work done, W is equal to work done, W is equal to nRT, right? Natural log of V2 by V1. That is final volume by initial volume. If the gas is going from a volume V2 to volume V1, then we'll have, V1 to volume V2, then this is how we write. And also we know that for an isothermal process, PV is a constant, right? Just see here, we have just learned. Have a look here, class. This one. PV is a constant for an isothermal process. Temperature is not changing. So we'll have P1 V1 is equal to P2 V2. This implies V2 by V1 is equal to V2 by V1 is equal to P1 by P2, correct? So instead of this V2 by V1, you can also write nRT log of P1 by P2, right? Now class, note down a question. Note down a question. A gas expands, right? Such that its temperature remains constant. Temperature does not change. Its temperature does not change and is equal to T naught. Its temperature is T naught, right? And its volume becomes e power 5 times. E power 5 times. Volume becomes e power 5 times. Number of moles N, number of moles N is given by 20, right? Number of moles N is given by 20. Find out the heat supplied to the system. Yes, class. How will you go about it? So let's write the given data. Let us take the help of Atul. Atul, can you just help us with this question? Yes. Yes, Atul. So just let me know what are all the data given in the question. We'll accordingly solve. Yes, Atul.
Yes, sir.
Yeah, tell me.
It is given that the temperature change in temperature is 0.
That is, we are given, first of all, we'll write all the given data. What is the temperature constant and equal to? Temperature.
T naught.
Okay, so temperature is T naught. Great. So class, this will be our pattern, right? So always we'll write what is given to us, what needs to be found out, what we already know, and the answer will automatically come. See? Okay. What else is given?
And its volume become e to the power 5 times.
So its volume becomes e to the power 5 times of itself, right? So let's say
Yes, sir.
initial volume was V naught, it becomes e power 5 V naught finally, right?
Yes, sir.
Number of moles is given as 20, right? What are we supposed to find out?
Q of the system.
Or the given
The
to the system,
heat given to the system. Yes, sir.
right? Okay. Any idea, Atul, how should we approach this question? What should be the length and breadth or whatever is coming to your mind? Yeah.
Mm, no, sir.
No worries. Just anything that comes to your mind. Random thought about the question from the formulas we have read just now. Maybe formula based or approach based, whatever comes to your mind. What are we supposed to find out? What are we supposed to find out? Heat,
Heat given.
right? So just
Yes, sir.
from here itself, see, I'm telling you the approach, how to approach a question. See what you are asked, first of all. Okay, I need to find out what is the heat. Do I know any formula related to heat? Yes. Try thinking about it.
Yes, sir. Delta Q equals to delta U plus delta W.
Right? This is one. There is one more
Yes,
formula,
sir. Yes, sir. Delta Q equals to
NC delta,
NC delta T.
right? We know two formulas right now, such that one
Yes, sir.
says one is NC delta T, right? And the other is this one, right? Now,
Uh,
since
yes,
this
sir.
is a constant temperature process, so maybe writing
Mm,
this one would not work, right? Let's see if we can find out the expression for heat energy via or change in heat energy via this expression, right? Okay. Now, do we know anything else? Do we know something about delta U for a isothermal process?
Isothermal process. Delta U is equals to delta W.
Think again. Delta U for an isothermal process is, check it out.
0, 0, 0, 0.
Ah,
Yes, sir.
that for an that for an isothermal process, change in temperature is zero. For an isothermal process,
Mm,
change in temperature is zero. And since internal energy is a direct function of temperature, so if temperature does not change, internal energy is also not changing. When
not
something
change.
is not changing, the delta U aspect of it will be zero, right?
0.
Change is zero.
Yes,
Change
sir.
in internal energy is zero when temperature is not changing. So I can take delta U as zero. Why?
0.
Because delta T is zero, right? Since
Yes,
delta
sir.
T is zero. So this will give us that delta Q is nothing but delta W, where what is
W.
delta Q? Delta Q is heat given to the system,
Given to the system.
found out,
Yes,
right?
sir. Yes, sir.
What about delta W, Atul?
Change in work done.
One more aspect,
Work done by the
work
system.
done by the system in an isothermal process, right? What is its value that we have just read? Have a look. Work done in an isothermal process is given as, yes, read it out.
Work done by, yes, sir.
Uh-huh.
W equals to nRT log V2 by V1.
Absolutely correct. nRT log V2 by V1. Let's substitute that here. nRT log V2 upon V1. Do we know V1 and V2 by any chance? Do we know T? Do we know N?
Yes, sir.
Try
Yes, sir.
substituting. Yes, tell me. How
V2
will
is V2 is e to the power 5 times V naught and V1 is V naught.
so let's write. And what about N?
And N is 20.
N is
N
20.
is
What
20.
about temperature?
T is T naught.
Okay, so let's write it down here. We have the heat supplied to the system given by, we have solution, heat supplied to the system, right? Delta Q is given as delta W. Delta W is nothing but the work done, which is nRT log of V2 upon V1, which is nothing but 20 into R into T naught,
Team
right, times of log of what
E
is
to the power 5.
volume? E power 5 times V naught, right?
Yes, yes, sir.
And V naught is nothing but the initial volume which I have taken. We'll cancel them, correct?
Yes, sir.
Now we
Yes, sir.
do a log for logarithm, right? That log of, suppose we have in the base E and also here we have E. So log of E to the base E, whatever is in
1.
power, let's say A, then that A will come over here. Can we write this? So it's
Yes, sir.
A log of E to the
Uh,
anything to the base, same base cancels itself and becomes 1, right? So this
yes,
answer
sir.
will be given as A, correct? Right?
Yes, sir.
So same thing we are having here. Natural log
5.
to the base E, right? So we have 20 RT naught log to the base E of E to the power 5, right?
5.
5 will come
Mhm.
in front and this will become 20 RT naught into 5 log of E to the base E, right? And this value is
Yes, sir.
1, correct?
Yes, sir. Yes, sir.
Now, since this is 1, we will get the answer as
100 RT.
100 RT. Absolutely correct. So suppose you're given with options like RT naught or 50 RT naught, 20 RT naught, and 100 RT naught. So our answer will be 100 R.
100 RT.
Are we clear with the concept and approach, Atul?
Yes, sir. Yes, sir.
So rather than surrendering, so Atul, this is the thing. What most students do, whenever they come across a question, they will surrender. But see, you already knew the formula, right? Didn't you? We just discussed it. We just discussed it.
Yes, sir.
So when we know the formula, rather than becoming afraid of the question and surrendering yourself, no, don't do that. Rather try to think what is given, what needs to be found out. Do I know any formula related to it? And slowly, one by one, your brain will give you an answer and you will reach it, right?
Yes, sir.
Okay. So, Atul, can you explain it to everyone, the question and the approach in your words? You may take a minute. Go ahead. Yes.
Uh, yes, sir. We need to find the heat given to the system.
Mhm.
So for a
For a process which is isothermal.
isothermal. For a process which is isothermal, change in internal energy is zero.
Uh-huh.
So we will use the formula delta Q equals to delta U plus delta W, where
Uh-huh.
delta W is zero, and then delta Q will be equals to delta W,
Why,
and we know
why are they coming equal to each other? Because
because change in internal energy is zero for
why
an
is it
isothermal
zero?
process.
Why is it zero? Why is change in internal energy zero for an isothermal process?
Uh,
Because in
Delta T is zero.
because internal energy is only a function of temperature. So if the temperature is not changing, on an obvious note, internal energy would not change, right? So let's take a hypothetical example. Let's say U is equal to 5 into T, right? Or 5T square maybe, right? So what does this mean? The temperature won't change. Will U change? No, right? And for a
No,
constant
sir.
value of temperature, U will also will remain constant. Correct.
Constant.
So
Yes, sir.
in that terms we get this understanding that as temperature is not changing, so internal energy will also not change. Am I clear?
Not change.
Am I
Okay.
clear on this?
Yes, sir.
Okay, yes, go ahead.
Yes, sir.
Go ahead, Atul.
And then we know the formula for work done for an isothermal process, that is nRT log V2 by V1.
Mm-hmm.
We know the initial and final values of volume. We
Uh-huh.
will substitute the formula and get the answer, final answer, that is 100 RT.
Great. What is 100 RT? 100 RT is the amount of heat supplied,
Heat required supplied to the system.
and it is also equal to which is work done by the system, right?
That is, yes, sir.
Are we clear on this, Atul?
Yes, sir.
Properly?
Yes, sir.
Okay. Class, everyone who is clear with the concept and the approach, please raise your hand. Yes. Class, if you are clear with the concept and approach of this question, please raise your hand. Otherwise, if there is any doubt, feel free to ask. Yes. Okay. So I can see that everyone has raised hands. Thank you, class. You can bring your hands down. Let us go to the next part. Okay. Now, let me take a question for all of you. So class, you will see that I have started with questions on thermodynamic processes, right? So here's the question. The question says that you have a cyclic process, right? Which is given in this format. So I'll take the cyclic process in this manner, just a minute, but only half part of it. So right, let's say this point was equal to P naught, right? Here the volume is V naught, right? What happened? Or I'll take some values. Let's say, so this is a very category type of question and really important, right? So it's a pressure versus volume graph given to you, right? Both in SI units, right? Let's say volume is given in meter cube and pressure is given in pascals. Okay? Now you have pressure given in pascals along the y-axis. So here the volume is given as, at this point, volume is given as 50. Same is the case with pressure. Pressure is also given as 50. Here, volume increases by, or wait, just a second, class. Yeah. All right. So you have such a question given, right? And you're being told that this is point A, this is point B, right? This is point C, right? So this is how the first part of the cyclic process takes place. That is, a gas goes from A to B, right? Then it goes from B to C, correct? This point, right? This point is 60. 60 meter cube of volume of the gas. Right? So this is how the graph is given to all of you. And you're told that the graph is circular in nature. You're already told that the graph is circular in nature. It's a cyclic process. Then what happens is the gas returns to its initial value. So this way. In the next half, the gas returns to its initial volume, crossing the point D. So I'll repeat class. What happens is a gas goes from A to B, B to C, C to D, right? And then D to A again. All right. So you're being told find out the ratio of find out the ratio of find out the ratio of work done by the gas in the first half. So first half is from A to B to C, right, to the total work done by the gas. Yes, class. Get going. So let us take Karuna this time. So Karuna, yes. Can you, and the second half is basically from C to D to A. Yeah. So Karuna, can you try to figure out, or I have written one thing wrong here. This we are being told to the net work done. So ratio of the work done in the part one to the net work done by the system in the entire process. Or you can also be, if this question can also be framed in a way, what is the percentage of work done? So this is first part. Let's say, what is the percentage of work done in first phase of the system? First phase or phase one. Yes. Yes, Karuna.
So we know that for the net work done,
Uh-huh.
the internal energy is 0,
Okay. Think about it. Think about it. What is given first of all? Tell me what is given. Don't simply jump to the conclusion. Just see what is given. Yeah, tell me.
So the pressure at point A is 50.
In general, we are given with different data points, right? On pressure and volume graph. Can we see that? Right, Karuna?
Yeah, yes, sir.
We are given with different points along which the gas is passing, right? What are we supposed to find out from the graph?
Uh,
Tell me.
work done in the first part
Is
from
to,
A to B to C is to the total work done.
okay. So just try recalling. Can you relate work done and the graph? Try recalling from here. Yes, try recalling. Can you relate work done and the graph? Yes.
Oh, work done is
Yes, be allowed. Yeah, yeah, yeah.
work done is equal to integration of P dV
What else? What else do you call it? Yes, read it.
area under the graph.
Area under the PV graph gives you the work done. Now think on these lines, Karan. Yes, now try to think on these lines.
So we can find the work area under the graph A, B, C.
Okay, tell me how will you find it out? What is the area? Would you like
Uh,
to shade it? Yeah, go ahead and shade it.
yeah.
You can use this. Yeah, now go ahead. I'm leaving the pen to you. You can move the pen. Yeah.
No, so I can't.
Okay, are you not being able to?
Yeah.
Okay, I'll do it for you then. See. Tell me what is the area under the first phase? Is it this?
Yes, sir.
Sure?
Yeah.
Sure.
Yes, sir.
Acha, just give me 1 minute. Just give me 1 minute. Others try to figure out if Karuna is right, right? I'll give you 1 minute, Karuna, to think if you're right. I'm
Okay.
talking about the entire area under the curve. It means area between that curve and x-axis. Try to think just 1 minute. Yes. So, Karuna, can you recall, can you now tell me if you were correct or do you would like to correct yourself now? The
So
work
for the
done. Uh-huh.
first part when the system is moving from A to B to C, the
Uh-huh.
work done will be the area under the graph A, B, C only.
So, you have to also consider this part.
Oh,
That is the thing I was trying to tell you, that you need not only consider this area which we just told, this one. No. Why? Because see, have a look here. Whenever you talk about area, whenever you talk about area under the curve, so let's say we are talking about this, any curve, right? Any curve you talk about the area, then area under the curve always means the area which is stretching from the curve boundary until the x-axis. Super important. This is where most of the students go wrong. Right, Karuna? Am I clear
Yes,
with
sir.
this?
Yes, sir.
So the area under the curve is always the entire area from the curve which stretches from the curve until the x-axis. Are we clear with this, Karuna, now?
Yes, sir. Yes, sir.
Okay, now go ahead and tell me how will you find out the first one, that is area under the curve from A to B to C, the entire area, right? Apart
Yes,
from the
sir.
area of the semicircle, we have to also take this area, the area which I am shading now, right?
Yes, sir.
Correct?
Yes, sir.
So let's shade that area as well. Okay. Yeah. Now
Um,
tell me that area
so
quickly.
we can divide the parts into two semicircle and
Yeah,
one
yeah.
circle.
Divide it and do it.
Yeah.
Tell
So
me.
pi r plus,
Pi r square by 2, right?
yeah,
Pi r
r
square by
square
2 plus,
plus 15 to 50, 15 to,
sure, this is 80, right?
yeah, this is 80. So
How much
15
is
to
this?
80.
15 to
50.
80. Clear, Karuna?
Yes.
Sure?
Yes.
That is
Yes, sir.
length into breadth of the rectangle, right? This is
Yeah.
the area of the semicircle, area of the rectangle gives you, how much is the radius, by the way?
40, sir.
40. So we have r is 40. So we'll take this as pi into 40 square, that is 1600 by 2 plus 50
15
into
into
80.
80.
Are we right with this, Karuna?
Yes, sir.
Okay, so we get 800 pi plus 4000. Are we correct now, Karuna?
Yes, sir.
And let's say everything is the SI unit. See here, pascals and meter cube. So what should be the unit for work, Karuna?
So
Joules.
joules.
What is the unit for work, Karuna?
Joules, sir.
Joules. Okay, now tell me what should be the net area or net work done for the cyclic process. Okay, tell me one thing. If the area for the expansion is positive, if the area for the expansion is positive, then what should be the area for compression? It should be
Negative.
negative,
Negative.
right? So area for compression work, compressional work should be negative.
Negative.
So what happens is, Karuna, first we take this entire area, okay? Right? This is
Yeah.
the area under ABC graph. But when the graph goes from C to D to A, what happens is we have to ultimately subtract this area, the one below it. So what area remains then? What area
The
remains
circle.
then? The area of the
Circle.
circle, right? So now
Yeah.
area of the circle is telling us the net work done in the process A, B, C, D, and then again A.
Mm.
I will repeat, Karuna, that the net work done in first half and second half, that is work done from A to B to C to D to A, or I can just write this as A, B,
2A.
C, D, A. So for entire process, for this entire cyclic process, the work done is always area under that cycle, area under that cycle. That is the area under the cycle. What is the area under cycle this time, Karuna? In this
Uh,
case,
so
area of the
area
circle, right?
of the circle. Yeah.
Area of the circle. Tell me how much should it be?
Pi r square.
Pi r square. What is r?
40.
40. So your area should be
1600 pi.
1600 pi. Are we clear with this?
Yes, sir.
Sure?
Yes, sir.
Okay, so now report me. How will you report me the answer? The work done in the first half is to net work done
Net work done.
is equal to 800 plus 800
800
pi plus
plus 4000
4000 whole
by
by
1600
1600
pi.
pi. Sure, Karuna?
Yes, sir.
Check it once. Go through the entire calculation. Let me see. Let me know if we are correct once again.
Correct, sir.
right? So we'll
Yeah.
have this as one of the forms. You can again reduce it to pi plus 5 by 2. Have a look, Karuna.
So won't it be 2 pi? Pi plus 5 by 2 pi.
Okay, yeah. Now, is it correct?
Yes, sir.
Sure?
Yes, sir.
Okay, so I think Atul has sent the answer much before. Let me check. Okay. So Atul also has the answer, pi plus 5 by 2 pi. Absolutely correct, Atul. Absolutely correct. Karuna, are you sure of what you have told?
Yes, sir.
Okay, so will this ratio have any unit, by the way, Karuna?
No, sir.
Why?
Because work done.
Upon work done,
Work done.
have same units on numerator and denominator. Simple. Great. Okay, Karuna. Karuna, tell me, are you clear with this entire question and
Yes.
the way we have solved it?
Yes, sir.
Now, can you also calculate the approximate percentage? How will you do it? Tell me. Karuna, so one more thing for all of you, in fact, everyone in the class, that what happens is in the examination, sometimes you are presented with a little typical questions like this type. Calculate the rough percentage, right? So in such cases, don't get frightened. Rather, be very smart. Do smart work. So what should be the percentage, Karuna? How will you calculate the percentage of work done in the first process? Yes, first part of the process, phase 1, A to B to C. How will you find it out? How much percentage is it of the entire process? Tell me, into 100. Simple.
Yeah.
So we will write work done in part 1 upon total work done into 100, right?
Yeah.
How much did it come? See, pi plus 5
By 2 pi into 100.
by 2 pi into 100. Tell me approximate values of this function. Pi is nearly 3, right?
Yeah.
Pi is nearly 3 or 3.14. Let's take 3 for now, right? So 3 plus 5, how much does it yield you? 8,
8.
right? And what about 2 into 3? Nearly
6.
6. So 8 by 6 into 100, how much should it give you? 4 by 3 into 100,
Yeah.
right?
Yes,
4 by
sir.
3 into 100 is nearly 133%, right?
Yes, sir.
So this is how you have to do small approximations. So this is not the exact answer. This is the approximate answer, right? So what does this tell you? This tells you that the work done for the first half of the process was actually 33% larger than the total work done in the process, So this shaded portion is actually the work done in part 1, whereas now this red color shaded portion is the net work done, right? And the one which I've written in black is the work done in part 1. So this is telling you that this is telling you that the work done in part 1 is 33% more. So it is net work done, 100% of it plus 33% more. Are we clear with this, Karuna?
Yes, sir.
33% more work was done for the phase 1. Are we clear with it? Very clear.
Yes, sir. Yes, sir.
Pakka.
Yes, sir.
Okay, great. Class is the entire concept of calculating percentages, taking approx values, and also the concept that area under a PV graph gives you the work done. If this entire question and the concept approach is clear to you, please raise your hand. Yes, class. Please raise your hand if the entire question, the approach, and the way we have taken approximations is clear to you. If not, you can ask your doubt. Yes, Anupriti.
Sir, I think I have a doubt.
Yeah, Anupriti.
So, can we take to find the net work done? Can we find the work done in phase 1 and add it with the work done in phase 2?
Yes, absolutely. You can do
But
that.
then when I do that, the pi and pi gets cancelled and I get the answer as 5 plus pi by 10.
See, let's do it. How will you
If
find
I,
out? So we just got the work done in phase 1. This was the work, correct?
yes, sir.
Now, how about the work done in the phase 2? The work done in the phase 2 is the work below it, right?
Below it.
And
Yes, sir.
this one should be negative, right? This one should be negative.
Why? Why should it be negative,
See,
sir?
just have a look here. We just wrote because this process from C to D to A is
Yes,
a
sir.
compressive process, and in a compressive process,
Okay,
the
okay,
work
sir.
done is negative. See P
Okay.
delta V, right? So work
Okay,
done in a
okay.
compressive process is negative. Are we clear
Okay.
now, Karuna? Are
Yes,
we
sir.
clear now, Anukriti?
Yes, sir. Clear, sir.
So this work done below this graph is actually negative work. So you'll have to subtract this work below. So ultimately, from the graph, it's very evident that the work that you'll be left with is the area of the circle.
The circle. Yes, sir.
Correct?
So you
Total work should be area under the circle. Clear now?
Okay. Yes, sir. Clear, sir. Thank
Okay,
you.
great.
Thank you.
Okay, great. Yeah, yeah. So anybody else, any queries? Let me know. If no, we can move ahead. Okay, okay. So I presume that now that we have discussed it, the concept is clear to all of you. Okay, class. Then we'll accordingly move ahead. Okay, right. So class, can bring your hands down. Thank you very much. Let us take next question. Before I move to the next question, class, I'll quickly discuss with you all the concept of a Carnot engine, right? So a Carnot engine is basically one of the most ideal engines that can be present, and this Carnot engine, you all must have read this, that has its efficiency given in terms of temperature. So what is a Carnot engine? I'll draw a diagram here. We'll see the working of a Carnot engine and a refrigerator here, which is very useful while solving problems, right? Or the questions in your exam. So we'll have a Carnot engine, and here we have a refrigerator. So let's take a refrigerator and Carnot engine now, and we have in a Carnot engine, what happens is, first let's understand a Carnot engine. So in a Carnot engine, we have a source. This is the engine, let's say, and this one is a sink. So I'll write it here. This is source, right? This is sink, right? Whereas this one is engine. What happens is this. So I'll write maybe over here. This is the engine. So let's say source is at a higher temperature T1. The sink is at a lower temperature T2. So we have T1 is greater than T2. Now, the point of using an engine, first of all, engine is something which converts heat into mechanical work. Simple. Engine is something which converts heat into mechanical work, right? Suppose the engine in the vehicles which we use, the heat which is produced from burning the petrol, that gets converted into work done, and that work done is actually causing your vehicle, that is your car or two-wheeler, to move ahead on the road. That is the formula, that is the concept, that is the working. So now here, by the second law of thermodynamics, it says that there are two statements. One is Kelvin-Planck statement, right? And there is one more statement. So these statements actually try to tell you about the working of a refrigerator and that of a Carnot engine, right? So hello class, am I audible to everyone? Okay, if I'm audible to you, class, just raise your hand. Hello. Just raise your hand, class, if I'm audible. Just a quick check. Okay, I am. Okay, thank you. Thank you. Bring your hands down. Yeah. So I'll continue. Class, as I was saying, that we have a source, a sink. Each one has temperature T1 and T2. Let's say the second law of thermodynamics, according to the statements given by the scientists, that is Clausius Statement and Kelvin-Planck Statement, it tells you that if some heat is given by the source, right, by the source to the engine, let's say H1, right, and some work is done by the, or let's say instead of telling it H1, I'll write it as Q1. So some Q1 amount of heat is given by source to the engine. It converts it into work, but it cannot be completely converted into work done. It cannot be completely converted into the work done. Right? So this is what is called Kelvin-Planck statement, right? This is what is the repercussion of Kelvin-Planck statement. Kelvin-Planck statement reads out that it is impossible to design an engine. It is impossible to design an engine which extracts heat from a reservoir. This source is also called a reservoir because its temperature is remaining constant at T1. Irrespective of how much amount of heat you extract from it, its temperature will always remain T1. So T1 and T2 are constant temperatures. We are assuming this is an inherent assumption in a Carnot engine or a refrigerator problem, that irrespective of how much amount of heat you will take from the source, it will act like a reservoir. You take the heat, it will have the heat. If you take the heat, it will have more heat to supply. So it acts as a reservoir of heat. Whereas this sink is a place where you are giving out giving out some amount of heat. So I'll repeat what is Kelvin-Planck statement. Kelvin-Planck statement says that it is impossible to design an engine which extracts heat from a reservoir and fully converts it into work done without producing any other effect. So because of this, you cannot completely convert heat into work. Some part of it will be converted and wasted in the form of heat energy, which will be released into the sink. So the complete conversion is not possible. So you can express this as mathematically given by Q1 changes into work done plus some heat Q2 which is rejected into the sink, right? So you have W is equal to Q1 minus Q2. Now this, for an isothermal process, this value of Q1 by Q2 is given as T1 upon T2. Q1 upon Q2 is given as T1 upon T2 for an ideal gas. This is given for an ideal gas. Now class, there is a term called efficiency. Efficiency is what is the final output and what was the input. I'll repeat, what was the output upon what was the input into 100, correct? So what is the output? Why are we making an engine for doing work done? So work done upon what is input? Input is the heat, Q1. So W upon Q1 is giving me efficiency, right? And then into 100 is always there. So now let us write this efficiency in terms of heat. Work done we just wrote as Q1 minus Q2. So we'll have Q1 minus Q2 upon Q1. And we have just written that for an ideal gas, Q1 by Q2 is equal to T1 by T2, right? And therefore you will have this written as written as 1 minus Q2 upon Q1, and Q1 upon Q2 is T1 upon T2, Q2 upon Q1 will be T2 upon T1. Therefore, efficiency of a Carnot engine is given in terms of temperature for an ideal gas, where ideal gas is the working substance. So you also call this as the working substance. Here there is a working substance and ideal gas is being used as that working substance. So if an ideal gas is used as a working substance, efficiency of a Carnot engine is eta is equal to 1 minus T2 upon T1. 1 minus T2 upon T1. Right, class, note it down with you. Just the reverse happens when you are dealing with a refrigerator. Refrigerator works on the principle which was stated by Clausius, and Clausius stated a work or statement. It tells you that it is impossible for a self-acting machine. I will repeat, it is impossible for a self-acting machine. So it is impossible for a self-acting machine to, I'll just change it a bit. Okay. It is impossible for a self-acting machine to completely transfer heat from a colder body to a hotter body without the aid of an external agency. I will repeat. The statement was given by Clausius. It told that it is impossible to convert, to give heat. Let's say this is again the sink, right? This is again the source, each one at temperatures T2 and T1 respectively. Of course, we know that T1 is at a higher temperature, T2 is at a lower temperature. Now, the Clausius statement tells you that you cannot transfer heat from this cold body to the hot body, without taking the aid or help from an external agency. Some external agency has to help so that the heat coming from the colder body, let's say Q2, can go to the hotter body, let's say Q1. So some work has to be done on the system. This is how refrigerators work. So we can see that in the refrigerator, what we are doing is the source is actually the atmosphere. In case of a refrigerator, source is the atmosphere and sink is the colder temperature zone, that is the inside of a refrigerator. What does a refrigerator do? In a refrigerator, from the inside, you have heat being extracted, right? Heat is being extracted from a refrigerator and it is being thrown out. But this is not happening on its own. We have to give some electrical work. Electrical work means you have to supply electricity to a refrigerator, right? That is how you are giving some electrical work to your refrigerator, which is helping it extract more and more heat from a region which is already cold to a region which is already hot. So the point is simultaneous process. If a process is very or a process is very spontaneous, pardon me, if a process is spontaneous, in general we know that the heat should flow from a body at a higher temperature to a body at a lower temperature. So in general heat should be flowing from T1 to T2. But what are we doing? We are creating a very special system, and in that system we are trying to transfer heat from a colder body, to a hotter body. And how are we making this possible? By giving some external work. This is how, or this is what we called working of a refrigerator. That we are using some external agency to give work into the system. Here in this case, it is electrical work in case of a refrigerator which runs on electricity, right? So this electric work is allowing heat to flow from colder body to a hotter body, right? So this is how, class, we have framed this one. Everything will remain the same. See here, from here we have Q2 going in, W going in, right? So we will have Q2 plus W. They get summed up into Q1, correct? So we'll have this giving you Q1, right? So again, like the first case, we had W is equal to Q1 minus Q2. Just recall, just have a look on the left side, LHS, right? That W is equal to Q1 minus Q2. Same thing comes here. See here, plus we have W is equal to Q1 minus Q2, correct? Now, the point is that as you have this equation, right, similar thing will happen here also. But very, very important, you had the concept of efficiency. For a Carnot engine. But for a refrigerator, you no longer have the concept of efficiency. Rather, you have a concept of coefficient of performance. I will repeat. For a refrigerator, I'll draw it in the same pattern. For a refrigerator, you have the concept of coefficient of performance. Class, note it down, coefficient of performance. You also denote it by COP, coefficient of performance. There are different symbols to denote it. We can use, let's say, beta, right? So coefficient of performance, beta, is also very similar to efficiency. It is also output upon input into 100. Now class, this system can actually be, how do you calculate COP for this system, right? So the COP or coefficient of performance can be calculated in two ways. It depends whether you're using the system as a refrigerator, that is if the main purpose is to create some cold zone, or is to use it as a heat pump, So what is a heat pump class? Heat pump is nothing but the same process, but it is basically a heater, right? So where is it used? In the cold countries where we use a heater, right, to heat some place. What do? You take some energy from the electrical switchboard, right? And then you also take heat from the atmosphere and you supply it into your household, right? So this is what you're doing, right? In case of a heat pump. So it depends that what is your main purpose. If your purpose is to supply heat, the device will be called as heat pump. But if your purpose is to create a cold zone, right, then it will be called as a refrigerator. So based on that, you have the COP of a refrigerator given as the purpose was to extract the heat, right? How much heat have we extracted? We have extracted the heat Q2. So that is the output, because that was the purpose, extraction of heat. And for that, how much work had to be done? W, right? So output, input, that is W. Output by input. The output was the purpose. That is to extract the heat. How much heat has been extracted? Heat extracted is the purpose, right? Upon work done, electrical work done for it, which is the input. So output by input gives me coefficient of performance for a refrigerator. Again, write this as Q2 upon Q1 minus Q2. We know that Q1 is to Q2 is directly proportional to T1 is to T2. So this is given by T2 upon T1 minus T2. This is beta for a refrigerator. Very important class. Take it as a note with you. Right? Now, some students tend to memorize this formula. No, not a right approach. Memorize this entire concept if you wish to. Even better, understand it and be in a position to reproduce it whenever asked to. I'll repeat, rather than memorizing, be in a position to reproduce this concept, right? Reproduce this concept, because this is not something a rocket science, right? It is a very simple process, that output by input. Simple. What is your purpose or intended output? Your intended output is to extract the heat, right? So Q2, see here, extract the heat. You have extracted this heat extracted, right? Just put this, right? And in the numerator, upon input, what was the input? The input was work done, right? So put that in the denominator. As simple as that. Because not always you will be given with temperature and they'll simply ask you to find out the COP. No, that will happen when you are the luckiest batch of all. No, rather they will give you some values out of these over here. They'll ask you to find out temperature, or maybe COP will be given. You'll be asked to find out Q1 or Q2, something like this on this pattern, right? Okay, let's quickly come to what will be coefficient of performance for a heat pump. Coefficient of performance for a heat pump. So for a heat pump, coefficient of performance will be how much heat was supplied. See here, with respect to the higher body temperature or the hotter body, we will say how much heat was supplied. That is, heat supplied is Q2 upon how much work was done for it. That is W, right? So you will have, okay, I think this is Q1, pardon me. Here, have a look. Heat pump, how much heat was supplied? Q1 amount of heat. So Q1 upon W, which gives us Q1 upon Q1 minus Q2, simple, T1 upon T1 minus T2 is the heat given by the, or is the coefficient of performance for a heat pump. Super important. This is not a refrigerator. I'll just work it out. So yeah, this is not a refrigerator. This is a heat pump. Right. So I hope the concept is clear to each one of you. The concept is clear, right? In case yes, class, if this concept of Carnot engine, refrigerator, and how do you relate their variables, if it is clear, please raise hand. Yes. If not, you can bring your hands down. If it's clear, please raise hand. Yes, class. It's just a revision, right? So I am very hopeful that you all are clear with these concepts. So this is how we started today. Let's do a quick revision of what we did. One by one, we saw that what is the distribution of different topics and subtopics in this unit, right? We also saw how do we give the work done in terms of area under the PV graph, right? Relation between Cp, Cv. For a polytropic process, we saw what is the value of C, that is Cv plus R by 1 minus N, one probable question. Thermodynamic processes, we saw that there are 4 types of processes: isobaric, isochoric, isothermal, and adiabatic. Their specific heat capacity values being given as C, Cp, Cv, infinity, and 0 respectively. We also saw that how for an adiabatic curve, the slope is gamma times of isothermal curve, where gamma is called as adiabatic constant. We are going to learn about the gamma term in the chapter Kinetic Theory of Gases, right? Then for a polytropic process, see, we had PV par N as a constant. C is given as Cv upon 1 minus N. We'll solve very good questions based on this. I'll send you an assignment which will have some application of these concepts and some more, especially calorimetry based concepts, right? The one which I've told about in the initial part, right? So we'll have those concepts. Try solving. Any doubt, of course, we are going to discuss all the questions, so the doubts will be automatically cleared. Then we discussed some speciality about a cyclic process and isothermal process. For both of them, change in internal energy is 0, right? Then we saw work done values for an isothermal, isochoric, and isobaric process. As an end result, if you would like to add, do add that if we are talking about an adiabatic process. So if we are talking about an adiabatic process and we are going from volume V1 to V2, right? Then in that case, for an adiabatic process, the work done is given by W is equal to NR, right? Then instead, suppose we are talking about an adiabatic process which is for an ideal gas, then we have this as NR upon gamma minus 1, NR up into gamma minus 1, then we have T1 minus T2. T1 minus T2. This is the case for an ideal adiabatic process. Ideal gas, adiabatic process. NR T1 minus T2, where T1 is the initial temperature and T2 is the final temperature. Class, jot this down. Very one addition to your formulas. Then we had this one simple question we did, after which we did one more simple question. In both of the questions, the purpose was to elucidate you all how do you apply the concepts that we have read, right? So then we came across the concept of a Carnot engine and a refrigerator, and finally the coefficient of performance for a refrigerator and the efficiency of a Carnot engine, right? I hope all of you are clear, class, with the concepts that we have read today. We're going to continue all of this. This was first page, right? This was second, right? Then this was third one. This was fourth. This was fifth. This was sixth, right? This was seventh. This was eighth. This was ninth page. and the 10th page. So I hope all of you have understood well. Thank you everyone for being a part of the class today. Let us catch up. Let us meet tomorrow in the evening session, and there we'll be discussing some assignment solutions. I'll be sending you some assignments before tomorrow's class, much in advance, so that you have sufficient time to solve those questions. Those questions will be based on the past year questions that you've already solved, like always, and you'll have sufficient time. In case you're not able to solve any question, or you find a concept to be a little ambiguous at your end, no worry, you can leave that. You can solve the others in the class. In case we have not discussed that concept, we'll discuss it, as well as we'll solve all the questions, right? So class, I hope each one of you are happy with the content today we have read. It was a revision which I thought is a must for all of you, right? So on a basic note, we saw many things about reversible and irreversible processes. Reversible processes are generally very slow, right? And in nature, they generally don't exist. Irreversible processes are the ones which are obviously the other way around, right? What can be the application? We'll see in the questions which we'll be solving in the coming class, right? And also these questions will be sent to you in advance. Thank you everyone. Is there anything you want to ask or convey? Let me know. Yeah. Anyone, anything? Any queries, or you want to talk about something? Feel free. Okay. If not, then let's meet tomorrow evening, 5:15. Thank you very much, class. Thanks a lot. Thank you very much. Thank you, Anukirti. Thank you, Mahila. Thank you, Fire. Thanks all. Thank you.